Hi, my name is Ryan Thompson, and this is my submission for presenting on insertion sort. So initially, we are given an array with 4 elements, so n is equal to 4 here, and you may be, or you may not be, aware of the actual values held in each of these 4 positions, but there's a possible combination because it's an n choose k problem. So there's a possible combination of 24 different combinations on just these 4 cards. That assumes there's no duplicates. So there's no cards that can tie in there. So there is a best case and there is a worst case for these 4 cards. Obviously, based on the code below, the goal of this is to sort from lowest to highest value, so ascending order. So if you knew the order of these cards beforehand, or at least the values that were possible, the optimal order would be 10, 20, 30, 40. The worst order would be 40, 30, 20, 10, because you would have to go through the maximum number of times to determine if you've gotten the correct sort in place. And so the book will point out that the worst case is this quadratic function to estimate the runtime for the worst case scenario, and the best case scenario is a linear function. So looking at just those 4 cards, I tried to work out how many indexes you may have to move. So how many positions, given a random order of these cards, was the expected number of moves you would have to make to achieve an ascending sort. And the mode is 3 and the median is 3. So that's saying that given a random draw of these 4 numbers in random positions, these on average 3 times. So the minimum number of moves is 0. So that's your best case. That's a 10, 20, 30, 40 in those positions. The worst case being 40, 30, 20, 10, you would have to do 6 total moves to achieve the desired ascending sort. So with the average case around 3, approximately 3, and the mode and the median at 3, this is a symmetric, from my estimation, this is a symmetric distribution on this problem. So you should expect, with any random assignment giving to you, you should have to move 3 times. So that could be 1 index moving twice. It could be 2 indexes having to be moved 1 twice and 1 once, adding up to 3. So there is a distribution to how many moves will have to take place. And those number of moves will add up for the below levels. I think it's C5 and C6. So depending on how complex C5 and C6 are, or however long they take to implement, will modify that total runtime. But in general, the median and mode, only 3 indexes have to move. So starting at the first part, initialization, or the induction step, is because you're starting at I equal 2. So you're already assuming that the first position, which is a subarray of the total position, has the minimum value in it. And that's true because with only 1 value, it is the minimum. It's the complete set. So you've sorted the complete set. As this code moves through, it's every single time. So for every case, it's going to assign AI to key. So regardless of if you've sorted this correctly or not, it's going to go through those steps. So you're going to have this overhead in time anyway. So for every n, that line will be run. And same thing for the next line down, j equal I minus 1. It'll be run every single time, regardless of optimal case or not. So that's one of those fixed. Same thing with the bottom line of code down here. It's going to be run regardless. So that's another line of just pure overhead code. So if you modify any of these other sequences, you may get away with a lower overhead of this code sequence. So given this code sequence, there's a minimum overhead and then there's a maximum as well. So with j greater than 0, which is true, which is this whole conditional statement AI greater than key. So again, key got set to 10 because we're starting at position 2, and J equal I minus 1. So I is 2, J is going to be equal to 1. So the way that this insertion sort works is as I moves to the right to evaluate, to get a new key, to get a new position, J actually moves in the opposite direction. So depending on your length of time, that's another optimal versus worst case. They need to go in opposite directions to maintain that everything is evaluated throughout this whole sequence. So in this case, that whole condition statement is true. So A, J plus 1 gets assigned a J. J iterates down 1 position. But given that J is 1, that should error you out of the loop. There you go, you're evaluated. J is now 0, which violates the condition of the while loop. And we go down to one of these mandatory steps. A, J plus 1 is equal to your key that you set. And you need the key because otherwise you're going to keep overriding your index. And in some world, if you didn't store this off the side, you could wind up with the one value going through. So whatever your first index was, it would overwrite, and you would have, for index 1, 2, 3, 4, it would be whatever was originally set. Ours is 30, so it would be 30, 30, 30 all the way through. Now, key takes its position as dictated because of the conditional statement, and now we're going to go back up. So I iterates to 3. The new key is set. J is set again. So I is 3, J should be 2. There we go. And now we're going to evaluate the while loop. So is J greater than 0? Yes, it is. A sub J is greater than key? No, it's not. Now, again, one of the mandatory steps, A did not change it because it's I minus 1. No, the position doesn't actually change the value. All right, so now we're at the end of our sequence. So I is equal to 4, N is equal to 4. So this will be the last run through the entire sequence. So we'll see how many steps it gets evaluated. And we set the AI to key, so key gets set to 2. J is equal to I minus 1. Now it'll evaluate. J was greater than 0, that's true. Is 20 less than 40? True. Okay, so now 40 is going to get moved back to the end, or the position before it. All right, and as it goes through, it's going to evaluate, is the key less than 30? That's true. So now 30 being position 2 gets moved back to position 3. It will evaluate the 10 case, even though we know that's not going to be true. And that errors you out because it's not less than. So the condition is violated. So now you have this remaining position, and the key will be inserted into position 2. Now that leaves you with your optimal sort, 10, 20, 30, 40. And we're done. So that is insertion sort run through. And again, it's the subarray is true when we start this. It's maintained because at the end of every while loop, it's cleaning up and it's saying that for the subset that we know of, it is still true that they are in the correct sorted position. And then at the end, once it's gone through the entire index, the code is done and your array has been sorted.